explain who we are this afternoon. So first, Professor Joseph Logels from Catholic University of Louvain, with the first reviewer. Then we have Dr. Georges Cholon from LCPS Bordeaux, second reviewer. We have then, we go in the order of speech, Dr. Sébastien Lemonnier from Institut Saint-Louis, Institut Franco-Allemand de Recherche. Then we will have Professor Germain de la Fuente-Leitz from SiC, University of Zaragoza. Then we go to, if I'm not wrong, Dr. Laurent Parbagian from ESA. Dr. Marc Ferrato from Mercedes Company. Then myself, professor from Chemical Engineering Lab in Toulouse. And at the end, we have the two supervisors of your thesis, Dr. Francis Mori and Dr. David Gossin. I hope I have forgotten nobody. Okay, good. So the thesis has been prepared into SIRIMAT lab, under the supervision, as I said, of Dr. David Gossin and Francis Mori. And the title of your thesis is Additive Manufacturing of Silicon Carbide-based ceramics by carbide-based selective laser processing, from the functionalized powder to the final part. So Alejandro, you can go in.
Sir? Excuse me 1 second. I need to share the screen on Zoom. Okay. Thank you for the introduction. Actually, I don't know if you prefer to watch the presentation with light or without. How is better? Like this? Okay. So again, thank you for the introduction. Welcome everyone to my PhD defense. My name is Alejandro Monton, and thanks to the jury, my colleagues, my family, and my friends for coming here. So actually, the presentation is divided into 4 parts. First, we will see the introduction of the material that we are using. Then we will see the experimental technique, this PhD. And finally, of course, the research online. Next, regarding the experimental part, first we will see and explain the main technique that we are using and the process optimization of direct powder bed selective laser processing. Then we will explain the real and scientific approach of this PhD, the circuit modification of silicon carbide. We will see as well, and we will study the impact on the sintering behavior of this circuit modification. And finally, regarding the experimental part, we will see the powder bed selective laser processing of the circuit modified silicon carbide, and we will use spark plug sintering as cross-training. Then, third part is the conclusion of the project of today. And finally, we will see some future prospects and perspectives that we have to face. So the material that we are using is this work. It's a ceramic material, silicon carbide, that from a crystallographic point of view is one of the best known examples of polymorphism with more than 2 nanometers. The structure, the most popular structure of silicon carbide polytypes are 3 cubic, as we can see here, 4 hexagonal and 6 hexagonal. And specific, the mechanical properties are very similar among different silicon carbide polytypes. So regarding the manufacturing of silicon carbide, the ceramic material can be produced from a mixture of silica and some form of carbon glowing mass. And actually, if we regard to the phase diagram, silicon carbide, we can see that we don't have a melting point, but instead, silicon carbide decomposes into liquid silicon and solid carbon in excess of 2,545 degrees. And finally, the silicon carbide fabrication with a specific site is commonly made by a method called sintering, like for example, inverse boosted, the company involved in this project, which generally reaches temperature in excess of 2000 degrees. So probably, as you know, silicon carbide has unique characteristics such as higher modulus, low density, high level conductivity, and so on. And actually, this material has become more and more popular in the last decade due to these unique properties in our range of applications, such as aerospace and nuclear energy field sector, for example. But specific for some application, the component design can be improved by additive manufacturing. And within all the methods of additive manufacturing that we have, laser-based additive manufacturing has been expected to fabricate complicated shapes of silicon carbide in fluorescent layers. So here we can see a table with all the techniques according to the standard of additive manufacturing. This presentation is focused on powder bed fusion methods, and within all the techniques that we have in powder bed fusion method, the technique that we're using in this work is both called selective laser salt melting and selective laser sintering. But actually the principle is different. In selective laser melting, the powder is transferred from solid phase into liquid you complete it. And on the other hand, in selective laser sintering, the particle coalescence, the powder aggregate by diffusion, is accomplished by firing at an elevated temperature. But actually, in this process, here, we are not so sure about which strength we should use, because actually, what we can see, this is the technique that we are going to use, and after we will explain in detail, we can see that a powder bed is selectively laser processed, and actually both sintering, melting, and other phenomena could occur. So for example, if we are using just silicon carbide, since we don't have a melting point, we should avoid the use of selective laser melting. But if we are mixing our powder with, for example, silicon powder, which has a melting point, we shouldn't use selective laser sintering. So to avoid misusing of these two terms, we decided to create a new term to call this technique, which is powder bed selective laser processing. So regarding the setup of this technique, here we can see a general setup. The ceramic is in powder form and moves towards here, where a powder roller picks up the powder, and the powder is pumped onto a thin layer in the big platform. Here there is a laser which scans selectively the powder, following a pattern determined by the software of the machine. Actually, in general, this technique is divided into approaches, or two methods. Non-direct approaches, which requires use of binders and post-sintering is required. And on the other hand, direct approach, which post-sintering and bind is not required. But actually, this process is specifically complicated since silicon carbide decomposes into silicon and carbon, as we saw, in excess of 2,545 years. Now, regarding the state of the art of this material, silicon carbide, and this technique, at present, we can see that 70% of the references are related to a direct method and 30% to direct methods. And actually, if we look at the last strategies followed by authors, or researchers, and industry, for the additive manufacturing with powder bed selective laser processing of silicon carbide, initially they used a silicon and silicon carbide powder mixture. After the additive manufacturing process, they obtained a core of silicon carbide reforms. After, by performing polymer infiltration pyrolysis of a phenolic resin, which is a precursor of carbon, they obtain a core of silicon carbide carbon reform. And finally, by carrying out liquid silicon infiltration, they obtain a final reactive bond silicon carbide. So actually, it's still a challenge to achieve direct powder bed selective laser processing of silicon carbide in absence of additives, or for example, as we have seen, another initial powders. So as we have seen, here is the last strategy adopted by researchers and some industries. And actually, since we are obtaining at the end a composite of silicon carbide and reactive silicon carbide, we have a negative impact compared to, let's say, pure silicon carbide. And actually, at the end of the process, we have as well some residual silicon content that, for example, for some chemical application should be avoided. But actually, what's the original scientific approach of this PhD? Here, what we want to do, instead of using this silicon powder, we are going to graph a ceramic polymer on the surface of the silicon carbide. So what are the features or characteristics that we need in this ceramic polymer? Actually, this ceramic polymer will create
a stoichiometric silicon carbide coating via high temperature treatment in inert atmospheres. Then this grafted molecular layer will create reactive interface between the silicon carbide grains of the powder, facilitating diffusion and sintering. Next, this will produce the bonding of the ceramic particles without affecting the material phases of our parts. And actually, the main goal of this PhD is the manufacturing of full bed silicon carbide complex state by direct powder bed selective laser processing by reaching the properties provided by Marie Sklodowska-Curie of density, bigger hardness, and flexural strength. So what's the research line that we are going to follow in this presentation, in this PhD? First, we are going to study and optimize the process parameters of powder bed selective laser processing. Then we will see the powder surface modification with the study of the process parameters and the optimizations. After the next part, what we are going to do is to study the sintering impact of the surface modification by spark plasma sintering. And we are going to compare silicon carbide with the surface modified silicon carbide. And finally, we will use again the direct powder bed selective laser processing, this time to compare silicon carbide powder and surface modified silicon carbide powder. And we will use again spark plasma sintering as cost treatment for the manufacturers. So regarding the process parameters of powder bed selective laser processing, there are many parameters which are involved and they have an important influence in the final relative density part. But actually, there are 3 key points we need to focus to assure a successful manufacturing process. The first one, of course, is the laser material interaction. We need to assure that our material will be able to absorb the energy of the laser. So in our particular case, in this work, we will work in this wavelength. For example, if we are using metallic parts, we see that we have a good absorbance for this process, and we can work with. For other materials, such as, for example, oxide ceramics, we see that we don't have a good absorbance, and researchers have adopted as a strategy the addition of some additives to improve and enhance the absorbance, and now we are able to work with. And in our particular case, for carbide ceramics, we have a very good absorbance, so they are ready for this process. Next step is to assure a good powder flowability and a good bed packing mix. Specific to this work, we are using this powder, which has a certain morphology. And actually, regarding the particle size distribution, we can see that we have a P50 of 20 micrometers. But actually, here we know that a powder with a broad size distribution will increase the packing density. And moreover, the more spherical morphology in the powder, the better powder flowability. And actually, in this point, we didn't focus on mass. And at the end of this presentation, in the section of future challenges and perspectives, we will see that we have some work to do. And finally, of course, the laser parameters and scanning strategy. The 2 most important laser parameters are the laser power and scanning speed. Why? Because actually they determine the energy density that we are applying in the powder. Next, the layer thickness, which is the depth of each layer during the process. And actually here we need to assure that we have a short distance and we will interact all the depth with the laser. And finally, the adjacent distance, which is the distance between 2 adjacent laser beam tracks. Here we need to assure that we don't have a very big distance to avoid regions without treatment, and on the other hand, that we don't have a lot of overlapping. Otherwise, we could have a lot of heating and some decomposition. And finally, of course, the laser scanning strategy followed in the process, because actually they determine the distribution of the energy density, and as we will see, it will have a very important role in the optimization of the process. So now regarding the 3D printers that we use in this PhD, actually this one is not used in this presentation. We use the Orlas Creator 3D printer, which has, as you can see, a circular setup. And on the other hand, we have the Phoenix System Pro X, which has a back and forth configuration. Actually, 2 more important differences are the spot size, here is bigger. And moreover, in the Phoenix system, we have a polar compaction system that, as we will see, will have a very important role as well in the optimization of the process. So now, regarding the first experimental part, the optimization of the parameters of the powder bed selective laser processing, we were using 20 micrometers silicon carbide powder, and actually all the silicon carbide powder used in this thesis has been supplied by Marie Sklodowska-Curie. As optimization criteria of the parameters, we want to achieve the highest reproducibility of impact parts with the highest relative density at the end of the process. So here we can see in black the constant parameters of the process, and in red the parameters of the study that we delimited in a previous study. Moreover, here in the platform on the 3D printer, in the support, we glue a silicon carbide disc, a support for the manufacturing, to avoid the steel-ceramic interaction and be able to achieve a good manufacturing of the front layer, which are crucial for the process. So here we can see a diagram in which in the upper left corner and right corner, we have the points of maximum and minimum energy density. And by eye verification and with simulation we perform in collaboration with Turkey. Here in red, we obtain very unsuccessful manufacturing, and in green, we obtain some promising manufacturing. So then, regarding the optimization of this kind of strategy, here we decide to keep constant the other parameter to just see the effect of this kind of strategy during the process. Here we use 4 different kind of strategies. The first one, concentric in-out, following this path. Then, island scanning with hexagonal shapes, following this path. Linear scanning, following this path. Actually, each time that the laser arrives to the end, it's turned off and coming to the beginning and repeating the process. And finally, the zigzag, which is following this path. So actually, regarding the experimental results, we can observe how different the process is just by modifying this kind of strategy. Firstly, in the concentric in-out, we can observe a very specific defect pattern. Why? Because actually each time that the laser is changing the direction, there is a heat concentration and the production, the creation of some decomposition. On the other hand, in linear, we have the opposite phenomenon. Here, each time that the laser is arriving to the end, when it's turned on, there is a decrease in the temperature. We are not able to reach the sintering point, the sintering temperature of silicon carbide, and there is a bad safety between the layers. Next, in the zigzag strategy, we are avoiding these problems, but still we have some defects in the corners due to the very short scan depths of the laser with a lot of heat concentration and the production and creation of some decomposition. And finally, we have the hexagonal, which is avoiding all the problems that we have mentioned, and it seems to be the best one. So next, regarding the optimization of layer thickness and hatches distance, here we achieve, yes, a good reproducibility and a good relative density by using the parameters of 20 micrometers and 35 micrometers of layer thickness and hatches distance, respectively. And finally, we have to optimize, of course, the powder convection. To do this, we were measuring the geometrical density of the sample after the manufacturing process. So here, we use 3 different powder compactions. Here, 100% means that, for example, if the layer thickness in this specific case is 20 micrometers, we are going to compact all the layer thickness, 20 micrometers, here 10 micrometers, and here nothing. And actually, we're obtaining the best results in terms of geometrical density with 100% of compaction. And now, finally, that we have optimized all the parameters individually, we are able to manufacture, as we said, samples with a high reproducibility and the highest relative density. Regarding the microstructure of the material, here we cannot see clusters of particles or melting regions, and we cannot observe either specific defect patterns. If we zoom in, we can observe some porosity, but actually, if we compare these optimized parameters with our previous parameters, in details, with laser power 38 instead of 45, scanning speed of 100 instead of 250, and zigzag strategy instead of hexagonal, we can observe, of course, that here we have a reduced porosity. And in numerical values of density, actually here we are obtaining 53% of relative density versus 81% of relative density. And actually, now, regarding the material phases of this material, here we have the XRD spectrum. If we compare the XRD spectrum of the sample with the silicon carbide powder as received, in the powder as received, we can observe 6, 8, 15 electrical silicon carbide phases, exactly like in the pattern of the manufacturing process. But actually, we are observing some silicon carbide due to the composition of the process. So by performing the phase composition by the Whitlock method, Here we can see, as we said, that actually regarding the silicon carbide phase shift, we are obtaining qualitative similarities between the initial silicon carbide powder and the silicon carbide after the manufacturing process. And actually we have some silicon, some decomposition of graphite at the end of the process, because actually we have some partial decompositions due to high pitch inerrancy generated by the scanner strategy that we cannot modify. And actually here we will see in the future perspectives and challenges something that we have to do. So now we can assert the process viability of this optimization, because now we are able to manufacture complex shapes of silicon carbide. Specific sorbents, with this dimension, the fabrication time was 2 hours and 30 minutes. And we are able to manufacture as well lattice structures of silicon carbide that actually can be only manufactured with additive manufacturing methods and not with the traditional manufacturing methods. So from this part, we can obtain the next results. We have studied and optimized the process parameters of the powder bed selective processing. We have studied as well the effect on the scanning strategy. We have obtained 81% of relative density silicon carbide parts. We have observed some partial decomposition during the process due to some peaks inerrancy generated by the scanning strategy. And finally, we can confirm the process viability, because now we are able to manufacture silicon carbide components. So now it's time to introduce the technical scientific approach of this PhD. Now we have optimized this process, as we have seen, but actually what we want to do is to graft a pre-ceramic polymer, as we said, to the surface of the silicon carbide powder. So for this, we need to perform a surface modification, in which the silicon carbide pre-ceramic precursor is grafted on the grained surface of the silicon carbide powder. And actually, this is a potential method to improve the sintering behavior of this ceramic material. So the ceramic precursor that we are using in this work is the polyacetylene, which has a commercial name of CVD4000. The characteristic of this commercial ceramic precursor is that the CVD4000 is a carboxylene polymer, which is used as molecular precursor in the growth of silicon carbide by chemical vapor deposition. Moreover, this is a liquid compound, which is flammable, inert, and moisture sensitive, and highly soluble in solvent, and it's as well handled in an argon atmosphere. And finally, it has a silicon carbide ratio 1:1, suitable to form pre-ceramic polymer in a silicon carbide synthesis. So now, what we want to do is to know the mass of the polyacetylene of the oligomer that we need to graft all the powder. So for that, we develop the following model hypothesis. Firstly, the silicon carbide particles are more dispersed and spherical. Then, the formula of the polyacetylene, this one, has an index of 5. Next, the surface occupied by one grafted molecule is the surface projected by a molecule attached perpendicularly to the silicon carbide surface. And finally, the polyacetylene polymer can be only attached on the silicon carbide surface and not on a fresh molecular polyacetylene. And actually, by developing this hypothesis, as you can see in an analysis that I have prepared after I have created some extra content to discuss as well, we can arrive to this expression to know all the mass that we need to graft our silicon carbide powder. So now regarding the powder grafting experimental protocol, by reviewing the literature, we use the following protocol. Firstly, the particles are dried in vacuum in a vacuum oven at 110 degrees to remove physical chemically absorbed species. Then this suspension of polyacetylene, toluene, and silicon carbide is subjected to 5 minutes manual agitation to improve the oligomer solubility and homogeneity, and it's subjected as well to ultrasound bath for 10 minutes at room temperature. And actually, regarding the expression of mass, it's very important not to use an excess of polyacetylene during the process. Why? Because this could decrease the powder probability. So we wouldn't be able to use this powder, this ceramic, in an additive manufacturing process as powder bed selective processing. And moreover, this could increase the specific surface area, producing a change in the morphology, and the coupling agent would hardly penetrate into particle agreements. Next is the wet functionalization. Here we are going to transfer the suspension into a vacuum gas manifold under argon and subject it as well to magnetic strain for 1 hour at 60 degrees. Following a step, the suspension is again transferred to a rotative evaporator And here the tolerant is removed by operation under moderate baking conditions at 60 degrees. And actually after this step, we can take our silicon carbide in dry powder again. But actually, if we are using some excess of polyacetylene, it won't be a problem because it will be removed since the oligomer is sufficiently volatile to be transferred. Regarding the grafting process parameters influence, because for example, we were saying that we were using ultrasonals, we were using 60 degrees of temperature for the process. Here we were using the infrared characterization to know and to study the grafting efficiency of the process. So regarding the infrared spectrum of the oligomer CVD4000, here we can observe, we can distinguish two regions. The first one with the CH stretching and CH stretching, and on the other hand, with the CH scissor back and CH back twist. But actually, if we focus on the infrared spectrum of silicon carbide as received and surface modified silicon carbide, in this region, since we are using a very weak oligomer content, we cannot detect the signal of this oligomer, and yes, we can see the silicon carbide peak. And on the other hand, here, in this part, if we zoom in, we can observe the silicon hydrogen bond. That's why we call this peak like the grafting peak, and this peak will be used to study the graft efficiency of the process. So regarding the optimization of temperature, here we were using silicon carbide powder of 20 micrometers, and actually we were using 4 different temperatures: 80, 60, 40 degrees, and room temperature. And effectively, we can observe that in the silicon carbide powder, as you see, we can observe this peak after the process. So actually, regarding the intensity ratio, that's the ratio between the silicon carbide peak intensity and silicon hydrogen, the grafting peak intensity, we can see like at temperatures of room temperature and 40 degrees, we cannot observe an important increase. By increasing the temperature at 60 degrees, here we can start to observe, let's say, an important decrease in intensity ratio. But actually, by increasing at 80 degrees, compared to the other values, we observe a huge increase of the intensity ratio. But why we are not using 80 degrees instead of 60 degrees? Because actually, after the surface modification process, at 60 degrees, here we have the silicon carbide in powder form, but at 80 degrees, instead of having the silicon carbide in powder form, we are forming some silicon carbide plates because the temperature is leading to some cross-linking. And actually, since we don't have the ceramic in powder form, we are not able to use it in powder bed selective process. So moreover, we optimize more parameters. For example, regarding the ultrasound, we saw that sonication enhanced the effect on the graduation by increasing the weight ratio, the graft efficiency, the oligomer conversion, and the reduction of reaction time. Next, we studied as well that the large excess of oligomer that can be grafted and polymerized on the surface of the powder decrease the grafting performance, and it is reported in literature. And regarding the flexibility of the process, we have conducted a surface modification of 2 different silicon carbide powders with 20 micrometers, 2 micrometers by millimeters. And finally, after 6 months, we have observed, and 1 year of the powder stock at room temperature in our atmosphere, a reduction of 18% and 35% is detected in the grafting efficiency. So regarding the results of these parts, here we have seen, and we have studied the effect of the process parameters, temperature, ultrasound, and polygomeric weight. We have used infrared characterization to study the optimal conditions to conduct this process. Next, we have observed that the surface modification shows a good reproducibility. We perform this surface modification on 20 and 2 micrometers silicon carbide powder. Actually, the surface modified silicon carbide powder does not allow a big delay in time in its application. And finally, this is a method that which potentially will improve the sintering behavior of the silicon carbide, as we will see in the following section. So here now it's time to study the impact on the sintering behavior of the powder of this surface modification. So for this, we are going to use 2 different powders, 2 micrometers and 2 micrometers silicon carbide powder after the surface modification, and effectively we are going to evaluate the sintering behavior. Here we are using spark process sintering because actually this is a favorable method for sintering silicon carbide, as it is reported in literature. and actually provides a fast fitting and a short sintering. So actually, this is the setup of the stuff from the sintering. This is a sintering technique which uses pressure driving powder compaction, in which a pulse direct electric current passes through the sample. And actually here, with the powder, what we are going to manufacture are silicon carbide pellets with 6 mm diameters and 2 mm thickness. To understand what we have in the graphite die, here is the graphite die. First, we place a graphite foil, then we place a graphite die. After we put the silicon carbide or the surface modified silicon carbide inside the graphite die, and finally another graphite die here. Regarding the experimental path of temperature and pressure that we use for this process, we are starting at 600 degrees, reaching up to 2,200 degrees, and actually the pressure was still constant once the heating was starting with 50 megapascals. And actually, as we can see here, just in 20 minutes we can achieve and manufacture silicon carbide like this. So actually, this is a very rapid manufacturing step. So now, regarding the relative density of the silicon carbide versus the surface modified silicon carbide, here we observe a high reproducibility using the powder as received with a relative density of 91%. On the other hand, using the functionalized surface modified silicon carbide, the sample reaches relative density in the range of 93 and 93%, despite being very close to full densification. So actually, we are increasing in average 4% the relative density by using surface modified silicon carbide. Here, regarding the microstructure of the material, we can observe some porosity that is increasing at the edges of the material, and we can observe some brighter, darker areas. If we compare with the microstructure of the surface modified silicon carbide, again we observe some porosity that is increasing at the edges of the part, and again we can observe these brighter, darker areas, but actually we observe similarities between the both microstructures. But if we zoom in this part and we perform EDS scan analysis to know what we have here in the surface, what is these brighter, darker areas, we cannot observe any change in the composition. So actually what we have here are different crystallographic orientation of different silicon carbide polymers. So now regarding the XRD spectrum to know the phases of this material, here again the powder as received. If we compare with the silicon carbide after spectrum sintering, we can observe moissanite 6,8,15 raw material, like the powder can achieve, some graphite due to contamination of the graphite dye that we are placing in the beginning. But actually here we observe a new phase, silicon carbide 4,8, that is not present in the powder. If we compare with the surface modified silicon carbide after spectrum sintering, again 6,8,15 raw material, like powder as received, graphite due contamination, but again for 8 states. So actually we have similar material physics effective in both polymers. So regarding the phase composition again by random method, here we observe similarities with the silicon carbide powder and surface modified silicon carbide powder. And effectively, for the silicon carbide and surface modified silicon carbide after the spectrum sintering, we are observing some transformation from 6,8 to 4XR. But actually we are not able to observe this phenomenon in powder that we stop at 1,600 degrees. Actually, here we cannot observe this transformation from 6,8 to 4,8. Why? Because actually the spark plasma sintering process was interrupted before reaching the sintering silicon carbide temperature, and consequently no silicon carbide 4,8 transformation can occur as it is reported in details. So now we are going to use the silicon carbide and surface modified silicon carbide experiment that we stop at 1,600 degrees to study the synchronization of both polymers. So for this, here we can see the profile of temperature and displacement, and actually a change in the displacement curves, as we can see here, means dimension shrinkage of the powder. Specific for the silicon carbide powder, this is happening at 1,240 degrees. And for the surface modified silicon carbide at 1,060 degrees. So actually, we observe that the sintering process initiation has a difference of 180 degrees. But why? What is happening here? Actually, the graph molecular silicon carbide hydrogen is forming a reactive interface between silicon carbide polymer and actually it's facilitating the functionalized system. So finally, the sintering is typically facilitated using surface modified silicon carbide polymer instead of non-functionalized silicon carbide. So from this part, we can obtain the following results. First, we have densified a silicon carbide sample up to 91%. On the other hand, surface modified silicon carbide densified up to 96%. Remember, with the same structural machinery conditions. Next, the densification is always better in a range of 100% for surface modified silicon carbide compared with silicon carbide sample. And actually, the surface modification decreased the sintering start temperature at 180 degrees. And finally, the sintering is typically facilitating using surface modified silicon carbide. So now it's time to compare with the additive manufacturing technique, the silicon carbide and the surface modified silicon carbide. So regarding after seeing, that effectively with the surface modification, we are enhancing the sintering behavior. So what's the mechanism? Why we expect to improve the process with the surface modified silicon carbide in polymer selective process? Because actually, by thermal decomposition, due to laser reaction, we'll create the graft personate precursor. We will lose hydrogen, leading to cross-linking, and we create a solid amorphous polymer. Then, by continuing this loss of hydrogen, leading again to cross-linking, we will form a solid amorphous silicon carbide that will be converted into polycrystalline silicon carbide as it is reported in liters. Next, this grafted molecular silicon carbide hydrogen layer will create a reactive interface between silicon carbide polymer rings, facilitating diffusion of sintering. And finally, this will produce the bonding of ceramic particles without affecting the material traces, making the binding process unnecessary and actually fulfilling the original conversion into silicon. So regarding the parameters that we use for the silicon carbide to do this comparison, here are some of the parameters, and maybe you're asking why we are using 50 instead of 45 as we used in the beginning. Actually, after we can discuss, but at this point, we didn't start yet the collaboration with the colleagues from Turkey, and we have this value as the best one for the process. And comparing the surface modified silicon carbide, here we have exactly the same parameter, except for the scattering speed, where we are using 500 instead of 250. Why? Because actually here we were following the same protocol criteria to optimize the parameters. And we observed that by using this scanning speed, instead of this one, for example, we were reaching parts with highest reproducibility and highest relative density. In numerical values, actually, 65% of relative density versus 71% of relative density. So actually, regarding the microstructure of the silicon carbide after the process, again, we can observe a rough surface, no clusters of particles, no melting, no specific pattern defects. Comparing with the surface modified silicon carbide, again, no cluster of particles, no melting, no specific defect patterns. So actually, we have microstructural similarities at this scale. Regarding the porosity of the silicon carbide after the process, by performing X-ray microtopography, we are obtaining a total porosity of 32%, compared with interior values of regions of this part, 33 and 34, very close values. And in comparison with the surface modified silicon carbide, we obtain a total porosity of 29% with interior volumes. In the interior volumes, a porosity of 30 and 31%. So actually, here we are improving, we are decreasing, let's say, the porosity of 3% by using surface modified silicon carbide. But remember that we are using 500 millimeter seconds instead of 250 millimeters. And actually, I want to highlight that, for example, by using this scanning speed for the silicon carbide, we will obtain parts without reproducibility and with a lot of defects. Here we have the phases of the material, the XRD spectrum. For the silicon carbide, again, as we have seen, two, like the powder as received, and two due to the composition. Regarding the surface modified, again, two like the powder as received, and two phases due to the composition. So actually here we have similar material phases in the effective periods. Regarding the phase composition, here I would like to focus on the silicon content here after the process, because we can observe an important reduction by using surface modified silicon carbide instead of silicon carbide gold. Actually, we have a 2 silicon phase reaction factor, because remember here we are decreasing the energy density by increasing the scattering speed, and that's why we observe a smaller decomposition during the process. So the next step, once we have performed the additive manufacturing method and we have obtained our parts, we are going to use spark plasma sintering as post-treatment. Why? Because actually we can use this post-treatment to treat complex cells. Here we have the setup of the machine. Again, we manufacture 20mm silicon carbide and surface modified silicon carbide diameter pellets with this, with the powder surface, with the powder bed selective laser processing, with 2mm thickness. And actually, the graphite die, we are going to fill the empty space with graphite powder. To zoom in the graphite die, here again, we are going to place a graphite foil, then a graphite die. As we have seen, we are going to put some graphite powder. Then we will place the silicon carbide or the surface modified silicon carbide part manufactured by the additive manufacturing. Then again, some graphite powder. And finally, the graphite die. And actually, we are going to follow exactly the same experimental path that we used in the previous experiment. So regarding the microstructure of the silicon carbide after post-treatment, here we can observe, of course, a reduced porosity comparing this sample with the previous one manufactured by additive manufacturing. And very similar, here we can observe again for the surface modified silicon carbide a reduction in the porosity as well. So actually here again, we have some microstructural similarities at this scale. Next point is to study the porosity after the post-treatment, again by using X-ray tomography. So actually here we are obtaining 27%. If we compare before spark plasma sintering, 32%. So we are decreasing the porosity in 5%. And regarding the surface modification, 21%. Remember before was 29. So here we have a reduction in the porosity of 8%. So actually we have comparing the surface modified silicon carbide and silicon carbide, 5% difference of porosity, a similar value that we obtained before. And actually with spark plasma sintering, we are able to decrease up to 8% the final porosity of the sample. Remember, we can treat complex cells of silicon carbide. So next, we perform some preliminary mechanical properties, but actually here we have time just to test the silicon carbide and not the surface modified silicon carbide. We were using 17 samples with the dimensions. And actually, first, we wanted to study the flexural strands by using 3-point bending strands. So specific, we obtain a value of flexural strands of 137 megapascals. Remember, with a porosity of 27%, with a silicon content 15%. If we compare this value with the last strategies, the one that we were explaining in the first slide, of the additive manufacturing by laser sintering of reactable silicon carbide, we obtain a, let's say, similar value, despite the fact they don't have any porosity. They say they are obtaining full depth values with a similar content. So probably by decreasing this porosity, we could be closer or even with a better flexural size. But actually, if we compare with the value provided by Mercer and Rustek, we are still some far, and we have to work in this sense. Regarding the Vickers hardness, here we were using an intention load of 4.5 newtons, and actually we obtained a value of 2,200. Remember, with a porosity of 27% and silicon content of 50. Again, if we compare this value with the same last strategies adopted by researcher, they are obtaining, let's say, a similar value, but a bit smaller. Probably because remember they are obtaining a composite of reactable silicon carbide. So as we said, this has a negative impact compared to pure silicon carbide at the end of the process. And regarding the Vickers hardness provided by Mercer and Rustek, here we have a very similar one. So from this part, well, the results that we can obtain is that we have obtained silicon carbide and surface modified silicon carbide with powder bed selective laser processing with 3% final difference specification. Next, we have observed a 2% reduction factor of the silicon phase due to energy density decrease. This is in accordance with the sintering initiation reduction that we have seen in previous experiments. We use spark plasma sintering to further densify around 80% the samples. And finally, the silicon carbide, after additive manufacturing and post-treatment, exhibit a bigger hardness of 2,200 and threshold strength of 137 megawatts. So regarding the conclusion of the experimental parts of this project, we have studied and optimized the process parameters of power red selective laser processing. Now we can confirm the process viability because we are able to manufacture complex silicon carbide cells by this technique without post-treatments, without additives, and without winders in the initial polymers. Next, we have studied and optimized the water process parameters to graph the preserving precursors on the silicon carbide surface. We have studied and we have seen the enhancement of the sintering behavior due to this powder modification. For this, we use sparkle sintering to densify up to 91% the silicon carbide powder and up to 96% the surface modified silicon carbide by sparkle sintering with the same condition. And finally, we have manufactured surface modified silicon carbide by powder-based laser processing, post-treated by sparkle sintering, obtaining a 5% inferior porosity compared to silicon carbide and a 2-factor decreased proportion of silicon base, because remember we are decreasing the energy density. So regarding the future prospects and perspective of this project, first, the powder optimization. Actually, we were using a cell morphology in the initial powder mixture that decreased the powder formability on the packing base. So in this regard, what we have to do is, for example, spray drying shows the possibility of atomizing silicon carbide powder with a bigger final diameter and spherical shape. Actually, we are performing some preliminary experiments, and now we are able to obtain silicon carbide powder with a final size of 35 micrometers, and of course, the spherical morphology. Regarding the silicon carbide powder modification, here we are using wet routes, which require use of solvent and post-drying steps that are often energy intense. And actually, here we should explore dry routes, such as vapor-phase infiltration, because they don't require use of solvents for post-drying steps. And actually, this vapor-solid interface has no surface tension, facilitating conformal modification of all exposed surfaces. Next, regarding the machine setup and process parameters initiation, here we have observed some decomposition and formation of defects during the process due to high temperature gradients induced in the surface by material laser interaction and the scanning strategy. So in this regard, we need to design a new scanning strategy and a new 3D printer adapted to ceramic materials with an adequate preheating system. And moreover, we should elaborate more complex shapes to know and study the limits of spatial resolution and density of this technique. And finally, regarding the characterization and mechanical testing, we perform just some preliminary post-treatment and mechanical testing. So here, of course, we need to measure the mechanical properties because we don't have time of the surface modified silicon carbide after the additive manufacturing process and sparkle sintering. And we should create a new standard of ceramic additive manufacturing because at the present we have no information. And moreover, we should perform more accurate analysis of the microstructure, such as to know you have an isotropic RPM or an isotropic part, to study the surface roughness and transmission electromagnetic. So thanks to everyone who made it possible to help me out during this PhD, my director of thesis, all the technicians, my colleagues from battery printing, and of course people from Mersen Boosted. So thanks for your attention, and I'm open to any questions you may have.
Alejandro Monton was the dynamic presentation. So now we will start the discussion with the jury. And we will start with the first reviewer, Professor Bruegels.